Often in science and engineering, it's important to describe the happenings in the world around us in terms of physical quantities. If we want to describe an object's motion, it's clear we're going to need a physical quantity that says something about space. We can use length for this purpose. It's also pretty clear that it will be important to specify time as a physical quantity to characterize motion. Less obviously, we'll typically need a third quantity which describes a physical property of the object itself. Roughly speaking, the amount of matter the object contains. For this, we will use the physical quantity of mass. A little bit later, we'll discuss why mass plays a key role in understanding and predicting motion. Now, length, time, and mass are considered the basic physical quantities we need to describe motion because almost all other physical quantities we'll need for motion can be systematically organized in terms of these big three as part of a process we call dimensional analysis. In this process, basic quantities like mass, length, and time are considered fundamental dimensions, meaning they can't be described in terms of any other physical quantity. And the dimensions of other physical quantities can then be expressed as products and/or ratios of the fundamental dimensions. Dimensional analysis is a very useful tool for us to keep in mind. For example, if we want to check whether our answer to a physics question is meaningful, we can examine, separately, the dimensions of the left and the right-hand sides of the equations we used to obtain our answer. Physically meaningful equations must have the same dimensions on both sides, so dimensional analysis can help us determine whether we've made some kind of mistake in our work. Now, when we go about measuring motion quantities, we will need a set of standards, or units, to help us compare our measurements. In this course, we will use SI units, which are commonly encountered in science and engineering. In SI units, each of our fundamental dimensions has a corresponding fundamental unit, and the units of all other physical quantities can be expressed as products and/or ratios of the fundamental units. Dimensions and units are closely related. For example, the process of checking our units for an equation is similar to doing dimensional analysis on the equation. However, it's good to keep in mind the distinction that units refer to a particular way of measuring physical quantities, and dimensions refer directly to the physical quantities themselves. We will frequently need to handle measurements expressed in units that are different from the SI system, so we'll need to be able to convert units. A good way to convert is to multiply by ratios of equivalent units and then canceling like units until we obtain the measurement in the units we desire. Whenever we work with units, it's good to try to use the units to help us develop a sense of scale, how fast or how slow, or how large or how small are the quantities we happen to be dealing with. We know from common experience that a sense of scale is important. For example, if we happen to be standing in line for something, then we know that there's a big difference between waiting for a few seconds, or a couple of minutes, or a number of hours, or for several days. Here's a good way to start developing a sense of scale for our work here. Whenever we get an answer, expressed in some units, to a particular problem, let's try to categorize the answer as being something that's either at a scale we run into in everyday life, or at a scale much larger than everyday life, or at a scale much smaller than typical for everyday life. If we practice this enough, pretty soon we'll start doing this almost as second nature, and it will be helpful as a quick check to see if our results are in the right ballpark.